Quasar. So here I saw this one plot where this is from the 2013 paper, and here uh, they have plotted something called the covering factor. This the covering factor basically defined from the how much part of the quasar is blocked from the view from the observer. So if your dusty torus structure is quite large, if it is covered most part of the observer, then the covering factor will be more. So it is defined as the infrared luminosity to the bolometric luminosity. So if you have a bigger torus, then you have a larger infrared luminosity. So we have a bigger, like larger covering factor. So they have said, so this guy has used like sample of sources, and they have measured this covering factor for low and high redshift sources, and they see some kind of trend, which is, and for the lower redshift the covering factor is low, and for the higher redshift it is high. So that means we there is some kind of evolution in this torus structure, and because as you go at high redshift, it is covering more part of the source, and we are, as an observer, we see very less part of this source. So so this kind of trend is actually not good for the cosmology, so we have to first resolve it. So for that, we in one of our work we have developed one tau model where we uh, where we try to see how the change in the covering factor can relate to the torus parameter and the viewing angle, and how it can affect the cosmology. So here we have shown this torus, and this is sigma is basically the opening angle of the torus, and there is the observer which is looking at viewing angle I. So from our calculation, we found that if we know so for the lower redshift sources, we know the exact structure of the sources, but for higher redshift sources, we do not know. But from this particular study, we see that there is some kind of evolution. So we want to know, if you don't know the structure at high redshift, then if you are assuming the structure of the low redshift sources, so by assuming this structure, how much error we can make in the cosmology. So here here we assume that, let's say at lower redshift sources, we know the correct luminosity distance of the source, and we know the correct structure. Then if you are using the same structure for a high redshift source, then how much error we are making in the luminosity distance. So here in the plot, I show the the opening angle for high redshift sources and for the low redshift sources. So for low redshift sources, it goes till 45 degree, because for the low redshift sources we exactly know the structure of the source, and we can measure the opening angle of the source. But for high redshift sources, we do not know the structure, so we have a like full range from, let's say, above 30 degree to 90 degree. So we see that if the half opening angle of the torus is at high redshift, if the half opening angle of the torus is less than 45 degree, then we underestimate the luminosity distance. Sorry. Yeah. So if for the high redshift sources, if the opening angle is like 45 degree, less than 45 degree here, then we see the luminosity distance here, which is like below zero. So that means we kind of underestimate the luminosity distance if we using the same geometry at low redshift sources. But if you go at higher, above 45 degree, if you're considering the sources at high redshift has a like viewing opening angle above 45 degree, then we are kind of overestimating the luminosity distance. So now from here we try to estimate the error in H naught. So we are kind of using the luminosity distance, error in the luminosity distance, to estimate the error in Hubble constant. So if we assume that at the lower redshift, we know the structure of the source, we know the cosmology, external lambda CDA model, then by using that omega m and the luminosity distance at lower redshift, how much error we can make in the luminosity distance at higher redshift and in H naught also. So here I show in the plot. So the error in whole parameter space is around 20%, and if the opening angle of the torus at high redshift is actually order of 40 degree, then we kind of then the error could yeah so if the at high redshift, if the opening angle is around 40 degree, then we are making the 8% error in h naught. And if the error can be both positive and negative, so the total we can make the 16% error by measuring the h naught if you do not know the exact structure of the sources at high redshift. But so the thing is, like, for from the supernova 1A, the result claimed by the supernova 1A proposed the 1% error in their measurement. So if you want to achieve those kind of precision with the quasars, then we have to be very careful about measuring the we have to very careful about the viewing angle issue, because the sources are kind of changing their viewing angle as we go from low redshift to high redshift sources. So I would like to add a comment here. So that the error is just an approximation, and it can be modified in future by considering more appropriate model of torus geometry and measuring the viewing angle of individual objects, which will constrain much better the parameter space. So in the next work, what we did was we kind of tried to measure the viewing angle of the individual sources, and so we consider the sample of sources, and we kind of constructed the broadband SED from here X-ray to optical UV and infrared. And to model the different part of the SED, we have used the different model. For the X-ray and optical part, which is coming from mostly the accretion disk, we use some kind of models called the AGN model. And for the infrared model, we to explain the infrared data, we use some kind of torus model which have the viewing angle as a free parameter. So we kind of so in our sample we have around 90 sources. So we kind of do the modeling in expect for all the sources by uh, and try to measure the two parameters, the viewing angle and the optical depth T. The optical depth is directly related to the opening angle of the torus. So by measuring these two parameters, we try to see if there is any evolution with redshift or with the torus parameter. The sample that we have collected has a redshift range of around 0 to 4, and then we have also checked if there is any trend with the black hole mass and the Eddington ratio of the source. So we measure the viewing angle for all the sources, and then we divide in the different redshift bin. So here we have divided in the 4 redshift bin, and similarly in the 4 mass bin and the Eddington ratio bin. And then the thing is, like, in the result we have very large error bar, and if we kind of make a 90% confidence interval for this plot, we see that all the data points, all the viewing angle at a different redshift kind of are within this 95% confidence interval. So with that result, we can say that in the observational data, there is no trend with the viewing angle. So if there is no trend with the viewing angle, then we can use these sources for a cosmological purpose. And so this is kind of some disagreement with the model that we have developed earlier. So in the model that I showed earlier, where we have some kind of uh, error, we are making some kind of error if you are assuming the same geometry at low redshift, the same geometry of the low redshift at the high redshift. But from the data, we see that there is no clear trend actually for the till redshift 4. So for high redshift sources, we do not know. So in the future, if you have more data, then we can uh, extend this plot for other high redshift sources and see if those sources differs from this relation. So from this particular plot, we can say that our cosmology is safe with the quasars, and we can use quasars as a standard candle to do the cosmology. So, so now I come to the part where how we are using these quasars to measure the cosmology. So we are using these two method, the emission line time delay and the continuum time delay. So this the measuring the time delay from the emission line is called the reverberation mapping. Is basically the measuring the time delay between the two different wavelengths which is causally connected, so that the time delay between the two light curves represent the light crossing time of the system. So on the left plot, I saw the structure of the AGN. So at the center, we have a black hole and then accretion disk. And then we, in some cases, we have a jet. And then we also have some structure here. It's called the broad line region. And then we have the dusty torus. So initially, we have the emission from the accretion disk that is called the continuum emission, which have all kind of disk emission, basically the thermal emission. And then this thermal emission can be reprocessed in this region, in the broad line region, which kind of produce the emission lines from this emission, from this continuum emission. So if you measure the both emission lines and the continuum, and if you can measure the time delay between, because there will, if so here as a observer, you first receive the continuum, and after some time delay, this light crossing time, you receive the emission lines. So if you can somehow measure the time delay between these two emissions, we can know the structure of the source and this size of this broadline region. So this is kind of the technique that has been extensively used to study these sources, quasars, and measuring the black hole mass and the broadline region size. And recently it has been used to estimate the distance of the source, because this distance of the source is an important parameter to do the cosmology. So similarly, in the other method is called the emission line, sorry, the continuum time delay, where we see the emission from the disk emission. We see the time delay between the disk emission, not from the line emission. Here we have a broad line region. Here we do not have a broad line region. We have just the disk emission. So in this case, it is assumed that there is a hot corona, which is a kind of high charged particles staying just above the black hole, and these are kind of relativistic electron, and they produce the X-ray emission from the inverse Compton scattering of the disk emission. So if you have initially we have a disk emission, disk emission, disk photon can get reprocessed here through the inverse Compton scattering and produce the X-ray emission. And then again, this X-ray emission can irradiate the accretion disk. So as we know from the accretion disk, we have the thermal emission, and the accretion disk follow this temperature profile, which is kind of change with the radius. So if this X-ray source can irradiate the accretion disk at different part, this this X-ray will be reprocessed here, and it can increase the disk temperature locally. And due to this increase in the temperature, it can emit the different emission than the other accretion disk. So similarly, if if this source irradiating the accretion disk at a different location, then it will increase the temperature locally here, and you see the different kind of emission. So if you somehow can measure the time delay between these two emissions, you can measure the size of the accretion disk. So this is the kind of method that has been extensively used for the study the accretion disk, actually for the disk structure and the size. And recently this method is also used to measure the distance of the sources and for further the cosmological purposes. So first I will talk about the emission line time delay. So in the emission line time delay, we see, if you just see the spectra of the quasars, we have, you will see the different emission lines. So we have the Lyman alpha, carbon 4, magnesium 2, and this H alpha line. And you see the power law, this power law is basically the continuum emission. So all the emission that you receive as an observer will be mix of the continuum emission, and on top of that you will have the emission line. And so we have to somehow separate it by fitting by using the different model to separate the continuum and the emission lines. So here we there are, and the other there is another uh, power law model is the called the red power law, which is kind of representing the starlight from the whole galaxy. Okay, so our purpose is to measure one of the emission lines. Is depends upon the actually the redshift, because we are only doing the actually measuring the emission lines in the optical or in the UV. So, but as you go with higher at the higher redshift, those emission lines will be shifting towards higher wavelength. So for the current, for a particular redshift, let's say for this one of the redshift, we have this mg2, which is like falling within 2000 to 400 4000 angstrom, which is in the UV, and we measure these emission lines and the continuum around it to estimate the time delay. So here I saw the kind of cartoon representation of how we do how it will look like from the accretion disk we have the continuum emission, and from the broadline region we have the emission line. So this the total emission is kind of mixed up, and we have to model it separately and then do the time delay measurement. So so the so from the study we found that so from the study we can estimate the size of the BLR, which is basically the time which is coming from the time delay. Basically the RBLR is the c speed of light into the time delay between the emission and the continuum. And it has been seen that they follow the specific relation with the as a function of monochromatic luminosity of the source. So, and this relation is called the radius luminosity relation, and which has some parameter alpha and beta as a free parameter. So, if we have the large number of sources, and if you can measure the time delay or RBLR for large number of sources, and if you know that their luminosity, we can, if you luminosity, and then you can make this kind of relation, which is kind of used to describe the these quasars in the radius luminosity relation. So, and then the question is how we can use this for the cosmology, this relation. So there are two ways. So one way is kind of discussed in this Bojana Cherny et al. In 2016, where they have solved the theoretically from the assuming the theoretical model, and they have this relation where the alpha is kind of 1.47 and the beta is around 0.5. And so to do the cosmology, we can use this expression where we have this luminosity distance and this intrinsic or monochromatic luminosity divided by 4 pi observed flux. So if you know the time delay, if you know the time delay, we can measure the RBLR. We know the RBLR. Then from this relation, we can know this luminosity, and this luminosity can be used here. And from the observation, we know the observed flux, so we can estimate the luminosity distance of the source. And since we are doing the studying the emission lines, from the emission lines we can easily measure the redshift. So if you have the redshift and the luminosity distance, we can make the Hubble diagram for these sources. And by using the Hubble diagram, then we can further estimate the H naught from them. The other method is like purely phenomenological, where we have the large number of sample, where we have large number of sources, and then you make you plot the emission line time delay in RBLR and their luminosity, and try to estimate the alpha and beta. So once you have the alpha and beta, then we can again use for a particular source, this alpha and beta will be fixed, and then we can use for a particular source RB to measure the luminosity, monochromatic luminosity for a particular source, and then can be used here for the to estimate the luminosity distance. So this is
Raj,
the yeah.
so may I ask a question?
Yes, yes, please.
So this radius
Sorry, I cannot hear you.
So this radius luminosity relation,
Uh-huh.
what is the origin? What is the origin of it?
So it is like if you measure the luminosity, like time delay for different sources, and if you have their luminosity, if we plot this together, we have some kind of relation between these.
Okay.
And this relation can be is a very standard relation actually, and it can be used for the different purposes. Like one of the purpose is for the cosmological model, and
Okay.
to do the cosmology.
So is there a theoretical understanding?
So yeah, so in this Cherny et al. 2016, they have did some kind of theoretical calculation to from where they have measured this value. So there is a two way. Like one is the like from the theoretical point of view, and so this is the different model actually. They have this one of their model is called Fredo model. They use to measure the BLR size and the luminosity of the source.
Okay. And I presume there will be error in, right?
Yes, yes.
So
So
so that fold into
yeah, so
your
that part,
DL.
yeah, so that part comes from here actually. That's what I was going to say here.
Okay, okay. Please go ahead. Yeah.
Yeah. So because we have the different sources, and so here we are using the time delay. So we have to be the error that is coming here is because of the time delay. So if you have the better data for a particular source, and if you can measure the time delay very precisely, then this all these sources should follow the this green line actually. It should be very concentrated, and currently it is like very sparse. So it is because we have the data is not so good. So so there are reason, like if so like on the right hand side plot you see there is a uh, uh, some technique has been used from here to here to reduce this uh, dispersion actually. And so for ideal case this should be like very narrow so that we can use for the cosmological purpose, and we have the less error in the result, and then the less error in the velocity distance and the cosmological parameter. So from this relation, yeah, so the from this relation, we have estimated the luminosity distance for the using the different sources, and then we have plot, since we know the redshift, so we have plotted the uh, Hubble diagram, and the blue line is basically the standard lambda CDM model using the H naught from this recent Planck collaboration data. So by looking this plot, it is clear that the all the quasars, whatever the quasars we have currently for this study, this standard lambda CDM model can actually explain, can fit this data, and there is no tension between the this Planck like CMB data, early universe measurement, and the quasars measurement for this particular for this number of sources. And similarly, you can also measure the omega m and omega lambda. And here we have shown that for the 1 sigma and 2 sigma error, and this radius luminosity and the the result from the Planck collaborations are like within 1 sigma. I mean, they are very close, but within 1 sigma error bar. So from this study, we kind of know that the quasars can be used for the cosmological model, and for the current result that we have, they do not differ from the early universe measurement like supernova. Like supernova differs very much from the early universe measurement. But these are the very exactly, we have a very low redshift here till 1.6 I think. And so if you go to the higher redshift sources, we do not know if how it will behave, if there will be any dispersion from the standard lambda CDM or it will follow the same relation. So that is the part of the future project actually. So we are also the part of the LSST science collaboration. So this LSST is a optical telescope that is going to be launched in few years, and it has a purpose of detecting the quasars for a very high redshift range. They predicted till actually redshift 10, and this LSST kind of observed in the optical band this UGR, IZY, these six filters. And if you want to do the cosmology with that, we have to see the this is the okay. So these are the filters in the background, and on the top of that, we saw the quasars spectra. So we see the different emission lines falls in the different band actually. So as we go to higher redshift, this emission line will be shifted towards right hand side. So since we are interested in the optical part, so we have to uh, select like those like that where we have the emission lines and the continuum in the different filters. So like in this particular case, this is at redshift 3 actually. So we have this carbon 4 emission lines which is full covering the R band, and then we have some continuum here which is covering the G band. So if you want to measure the if you
Ovik,
want to sorry.
no, please go ahead.
So if you want to study these sources at redshift 3, so we have to do the measure the emission lines for the carbon 4 in the R band, and in the G band we have to estimate the continuum emission. So so this is the the future project that we are involved, and we hope to see more number of sources there, and we can extend our diagram for a high redshift sources. So the other method is the Asian continuum time delay that I discussed earlier. So we have the from this relation, we have X-ray corona here, and we have accretion days. So we see some kind of time delay between the two emission coming from the inner part and the outer part of the disk. And if we measure the time delay between these two, we can do the cosmology. So, but there is a issue. The issue is from the theoretical prediction, the time delay that is coming from the this continuum emission follow this relation, the lambda to the power 4 by 3, which is shown here in this green color. And the problem is that this is the theoretical prediction, and from the data we see the higher time delay, which is not following which is basically following the lambda 4 by 3, but there is a difference in the normalization. So we do not know why this normalization is different in the observation and in the theory. So there is some kind of in the modeling, in the theory, there is some kind of issue that we should consider, or there is some issue in the measurement, like measurement in the time delay. That's why it is not matching with the data, not matching with the theory. And the other issue is uh, at around 3000 angstrom, we see some kind of jump, and this jump is kind of speculated as a the contamination from the emission line. So in the continuum time delay, we see the trend which is following this lambda 4 by 3, and in the if there is a and this time delay are like very small, within 10 days or so, and the emission line time delays are higher, and which is kind of showing the jump here. So this is kind of an outlier from this trend. So this is speculated as a emission from the broad line region, which is kind of contaminating this continuum emission. So if you want to use this as a cosmological purpose, so we have to first match this observation with the theoretical prediction. And the second point is we have to resolve this issue, because this should not be there. I mean, if this is contaminated by the emission lines, then our result for the cosmological purpose will change. So this method has been used earlier for to measure the cosmology in Collier 1990, and this is the expression they have derived that can be used to measure the luminosity distance. And if you know the luminosity distance, we can draw the Hubble diagram. So here we have the time delay measurement from the continuum emission, and then this is the flux measured from the these sources, and this X-ray is the X-ray luminosity of this X-ray source here. So there was attempt in 2007 to measure the H naught by using this expression and by using the edge in continuum time delay. And they measured the time delay. They measured the H naught around 44, which is like the one, around 1.6 factor smaller than the what is predicted from the early universe measurement from the CMB. So that clearly suggests that there is some issue. There is some issue that have to be kind of resolved before using this as a cosmological purpose. So these are the kind of the important problem that we have to kind of resolve. And so so we are kind of currently we are also doing some test for this, and we are kind of developing a model where we can somehow separate this part, which is the bump here, like in around 3,500 angstrom, and that is kind of from contamination from the broad line region. And if you remove this part, then we should have the lambda 4 by 3 slope here for all the time delay. And then there is also some issue at the higher wavelength in the actually in the infrared, but we are not currently bothering about that. We are focusing on this part, and in the future we will see if we can resolve this issue. And if we can resolve this issue, and after that if you do the cosmology, if then we will see if we are getting this exactly this value or the like the different value close to the supernova or from the this Planck collaboration. So, so this is all. So I will summarize the whole talk here. So the from our study, our test suggests that we can use quasar as a cosmological tool, and from the and we found that the yeah, we found that from the reverberation mapping technique, our result agrees with the supernova 1A till redshift 1.5, and after that it kind of differs. And for using the continuum time delay, we have to resolve the issue that I just mentioned, and we have to better understand the AGN structure and how the time delay can be measured very precisely to do the cosmology. And in the future, we will have the more number of sources from this LSST. So probably we'll have our Hubble diagram till let's say 5 or 6, and then we can see if it is still following the supernova 1A result, or it is kind of uh, differing from the supernova 1A. So this will be like very important part that can be used to constrain or resolve the cosmological tension in future. So thank you so much, and thank you for your attention.
Thank you, Raj. Any question from the audience?
Hi. Yeah, I have a couple of questions. Raj, can you go, first of all, yeah, great talk. Can you go to your slide where you had viewing angles estimated from the sample with some error bars associated with them?
Yeah, please.
Yeah, so then initially you said that it would make a difference, it would create some bias in the estimation of Hubble constant in the previous work.
Yes.
Is it that currently it's just that the error bars are big enough that one cannot probably measure those differences on this? Is that the right?
Yeah. So the issue is the same actually. Our since the first thing is our sample is like quite small. We had only 90 sources, and the other thing is while we are measuring the time delay using the SED modeling, and in the SED modeling itself we have not very good data points. Like in this case, one of the source at least we have the data points is like very covering the total SED, but in some of the sources is the data points are not so good. So the estimate that we got from the this fit, the viewing angle or the this torus parameter is not very precise. So in that sense, yes, if you have more bigger sample or very good data, maybe this error bar will be small, and then we can see some trend if it is there, as we see in our model actually.
Yeah, and a follow-up question on that is that you generally expect the error bars to reduce but just by increasing the number of samples, or do you think just from the model that you're using there is some fundamental degeneracy that might be enhancing these error bars?
Okay, so in this case, this is only the data actually. So
Okay.
there is no model involved here, right? Model in sense you are saying this model that I'm using
Yeah.
to feed the data. Okay. Yeah, so the thing, yeah, the thing is we have very large number of parameters and the data points. Again, there is the issue of data points, I would say.
Okay, thanks. And the last question is to do with the second method where you had computed the luminosity. Yeah, this exactly. So here you had also shown a plot of the computed, the next plot that actually shows how it's consistent with the Planck measurements. I think a slide, maybe a couple of slides after this.
This one.
Yeah. So the DL as a function of redshift. Yeah.
Yes.
So you had two different models for computing DL. Are they consistent with each other on this plot?
Okay. So here we have only one actually, because so here we have this data points, and from the data point we fit this relation, like, and we estimate the best fit actually. So this is purely the data actually, not from the theoretical model.
Oh, okay.
So this is just the data, and from the data we estimate the luminosity distance, and this is like following the standard lambda CDM.
Okay, thanks.
Any other question?
May I?
Sure,
Yes, please.
sure.
Raj, okay, so if I understand it correctly, please correct me if I'm wrong. So basically, from the time delay, you are measuring the radius, and
Yes.
then from that radius, using this relationship, you are getting the luminosity, and using that luminosity, you are calculating DL.
Luminosity distance, yes.
Okay. All right. So I mean, for low redshift, where you have a lot of measurement of a lot of the measurement of the ACD, and you can very well measure the ACD for couple of samples, couple of objects. So this relation, this radius and the luminosity relation, so this is like very precise relation, and this does not evolve as a function of redshift. That is you are assuming, right?
Yes. So here you see, if I, yeah, here we do not have the redshift information here, but this is for the low redshift actually, because the time delay measurement, if you go to the higher redshift, we do not have the good data that we could measure the time delay. So all the sources that is shown here is the low redshift sources actually.
Right.
So yeah, that is, you are right. Like if you go to the higher redshift, there is a possibility that this relation might not hold. So
Right. So then, I mean, the whole calculation again, like, need to take care of its evolution
yeah,
as
so
well.
I think then there would be some different relation probably, and then so this, like, it would be some kind of radius luminosity, but with the different alpha and beta, I would say.
Okay. Yeah. All right. Thanks.
Any other question?
I can ask another quick
Yes.
question. And this is just a very naive one on the histogram that you showed right in the beginning about cover fraction and how it suggests an evolution with redshift.
Yes.
How significant is that? This is from me coming because I have really no idea about the absolute numbers here. Is it a significant difference? And also, if you say subdivide these samples into even finer redshift bins, do you also see evolution within those?
Yeah, so the thing is here, like these are from the SDSS sources, and in the SDSS, we have like quite large redshift range, but in this particular study, what so from the SDSS also there are two, the sample is divided into the redshift bin. Like if you make the histogram of all the sources in terms of redshift, you see the peak around between this redshift and this redshift. That's why it has divided into two part actually by using this quasar sample. And so, and he is also the covering factor that is measuring using the data actually from the different telescope and doing the ACD modeling and broadband ACD modeling and measuring the luminosity actually. That is the way that people measure. So in that sense, if the data is not good, then we do not have clear, I mean, the good, like not good estimate of covering factor, then this cannot be like, then there is a possibility that we would not see the like some evolution in the redshift plane. But here they have only the two redshift planes. So I don't know if they like, if you divide in the final binning, if you still see the redshift because if you still see the trend, but the values are actually significantly different here. If you see, that was 1.4 actually, and this was in minus 0.4, and this is some 0.1 or something. No, 0.0 something. This is in the log. So the values are like quite significantly different, but dividing in the final binning, I don't know if it will like resolve the issue.
Okay, thanks.
Yeah. May I follow up with Saurabh's question? So,
Yes.
I mean, please tell me if I'm right. The way I understand, Saurabh, like this is when you are talking about covering factor. So from high Z to low Z, the AGNs will evolve also. In a sense, it will have more, probably accumulate more dust. I'm not sure. I mean, if I'm
Yeah.
wrong.
So
So
that's the
then,
thing, right? This relation suggests that if you go to the higher redshift, at least this result suggests that if you go to the higher redshift, the structure changes and the covering
yeah,
factor is higher. So that means you have the torus structure, which is bigger torus structure, which is covering more
yeah.
part of the source, and you are as an observer you see very less part and very small beam angle.
Right, and so that is consistent with the idea that, I mean, the AGN over the time they evolve, and a lot of the things settle down over the time, maybe. And
Yeah. So the thing is like in our model, when we try to test if this will affect the cosmological result, we by using this we found that we could make, if you are assuming the geometry of the low redshift sources, and if you are using the same geometry at high redshift, you are making some kind of error because at
right,
high redshift we do not know the exact structure of the source. But from the data we have the redshift, the the sources still redshift 4, and from there that result we see like here we are not seeing any kind of evolution in the viewing angle. So the viewing angle is, if your viewing angle is changing, that means the covering factor is also changing, but we do not see the much like, at least in this part we do not see much evolution. So
okay. Yeah, but the error bars, I mean, same.
yeah, that is true, that is
So
true.
those point that, yeah,
So
error
that
bars
is
is
also
really,
like this. The error bar is from the different reason, like because of the low sample and the not very good data.
yeah. Okay, all right. Yeah, thank you.
Any other question? So we thank Raj, and we can stop here. Thank you.
Okay, thank you so much for everyone for attending.